Okay, so this is a brief introduction to path integrals. Now we know from classical mechanics that you can use the Hamiltonian of your system to describe your energy or your Lagrangian. And in quantum mechanics, we've been using it to describe our systems, and it gives us the eigenvalues and the eigenvectors of our system. Now there's no reason to believe that if they both of these, H and L, describe the energy of our system, why we can't use L as well. And you can, and the difference is that instead of giving you the eigenvalues and eigenvectors, it gives you the propagator, which is why we had previously a short introduction to the propagator. Now, H works fine for a lot of quantum mechanics, the Hamiltonian, but the Lagrangian is particularly useful in particle physics and in quantum field theory. Okay, so now let's go back first to the beginning, to classical mechanics in the 18th century. And scientists were trying to work out that if you knew the energy of your system and you had an object at T1 with a kinetic energy inside a potential V, would you be able to work out where it would be at time 2? Using either your Hamiltonian, which is equal to T plus V, or your Lagrangian, which is equal to T minus V. Just a side note, outside of classical mechanics, this is not always T minus V. In electromagnetism and quantum mechanics, it's not always T minus V, but that's not important now. So how did they solve this? So Hamilton, who is actually more of a mathematician, came up with Hamilton's principle. It's a principle, which means that it's not proved, it's a stated. It's also known as the principle of least action. And what it says is that the path that your particle or your object will take is the one that minimizes, that's why principle of least action, or funnily enough, but there are a few cases of this, maximizes the action. Okay, now the action, if you remember, is defined as the integral from time 1 to time 2 of your Lagrangian with respect to time, where your Lagrangian is a function of your generalized coordinates, generalized velocities from where you can get your momenta, and time. Okay, so now if it's minimized, that means it's the derivative of s with respect to t is equal to 0. Now, we don't write it as you would expect as ds dt, normal derivative is equal to 0, and we don't write it as partial, just because that would be wrong, but we actually write it as delta s delta t. And this is purely a thing of notation to represent the fact that s is a function of L, and L is a function of other things. So s is a function of a function, and a function of a function is known as a functional. And so when you take the derivative of a functional, you use these deltas. So using this ds dt is equal to 0, we could, people were able to come up with Hamilton's equations and Lagrange's equations. And these were very powerful from the point of view of energy of solving problems. Now, I'm not talking about when you've got a ball with an energy of mgh, because it's at height h, you drop it, there's no air resistance, and it'll hit the ground with an energy of a half mv squared. This is not wrong, this is energy, it's not bad, but what it does is, because the potential is acting in one direction, if we think of force equals ma, and we start to think of forces. Now, apart from the fact that forces don't exist, in quantum mechanics, we need to be able to think about very complex potentials. And I don't know which examples you did in classical mechanics in second year or in honors, but it's possible to do very complex orbits around planets using Lagrange's equations or Hamilton's equations. There was a nice example when I taught it, I don't know if you do it now, of a wire with a bead on it moving along the wire. You can have a ball, excuse my great artistic skills, with a ball rolling around in it. You can show why a pencil is hard to balance, as opposed to, I don't know, a ball full of something very heavy. I mean, we all know naturally that that's hard to balance and that's not, but you can get out the equations of motion that to show that. Okay, and that's what path really means. Path is, I should say, more or less the same as the equation of motion. Okay.